Okay, so thank you very much for that very lovely introduction, Dean Wellman, and for welcoming me and inviting me to give this lecture at one of my favorite universities. It's been, I also ought to say, special thanks to Tomas Gambosi, who made that possible a few years ago. So I'm going to start with my pretty picture of the sun through an entire eclipse. I think it's really a very nice image, and it leads me to my start. I included a slide on Nelson Spencer with one point that Jim has not emphasized, which is I am at heart a theorist, despite all of the other things I have paid attention to in my career. But I really find that theory is represented in a lot of our space activities. And so I was very happy when I saw that Nelson Spencer believed in the importance of having theorists join in the planning and execution of space missions. Well, so I'm going to go on. I'm going to start with the solar eclipse of this year and ask the question, was it a big deal? And I would say, yes, it was. So the New York Times estimated that about 88% of American adults, or about 215 million people, watched the eclipse either in person or electronically. It's undoubtedly the most observed eclipse in the history of the world. Almost 7 million eclipse glasses were sold through Amazon alone. And these folks were watching the partial eclipse, waiting for the moon to blot out the solar disk as totality arrived. Then the sky above them became dark, and it was dark enough to see Venus. The sun's disk disappeared, glasses came off, temperature dropped noticeably, and the corona became visible. And that's really the start of my talk, because the corona is one of the important magnetically controlled structures in the solar system. To the naked eye, the eclipse looked something like the image I have on the screen. And I was there with 10 family members, so they were all enthusiastically joining me in this remarkable experience. Here is a picture taken by superimposing two photographic images taken with different apertures. And that allows you to see more than even the remarkable human eye can distinguish in terms of the range of light intensities. But the reason I show it is because it begins to emphasize the structure in this glow that extends above the sun. So these images were taken in Oregon, where the viewing was really fantastic. I looked on the web to find an image that would show even more of the magnetic structure. And this gentleman, Miloslav Druckmüller, is apparently renowned for capturing images of eclipses. And for this one, he used 161 images from 2 different cameras. And it just seems to me like magic. But what he found there was based, is the result of the magnetic structure of the sun itself. Otherwise, if there were just an atmosphere that was glowing around the sun, it would not have this kind of structure. To emphasize further the role of the magnetic field, I show you a prediction that was made a week ahead by a group in the Southern California area, headed, I have to say, by one of my former students, John Linker. And what they did was to look at magnetic maps of the sun, which can be produced by using special telescopic measurements, so that he knew what the magnetic field looked like over the entire surface of the sun. And from that, he was able to forecast the kind of complexity of structure of the illumination that would be observed a week later. And he got pretty much all of it, except, I think, yeah, he's missing something up here. Probably a magnetic development that occurred between the time he made his prediction and the time of the eclipse, or possibly because it was on the wrong side of the sun and they didn't have good imaging. So what's the camera imaging, and what is the prediction modeling? The structure is imposed, as I've already said, by the magnetic field of the sun, which is very complex. It is not like Earth's magnetic field that is so strongly dominated by a dipole centered near the center of the body and slightly, with its axis slightly tilted from the rotation axis of Earth. That's such a good model that we can use a compass to figure out where we're heading. But on the sun, the North Poles are all over the place. You would get totally lost if you tried to use a compass to find your way on the sun. But on the sun, the magnetic fields aren't visible. So what is it that we're really seeing? Well, we're seeing the gases that are present in the surroundings of the sun. They are highly ionized. Why are they highly ionized? Because they're very, very hot. The temperature is a couple of million degrees Kelvin. So they're really very hot, and when atoms get enough energy from thermal energy, they become ionized. So these gases are electrically charged ions and electrons. They're both signs of both charges, but they're as many positive as negative charges. But what we are seeing in the corona is sunlight scattered off of this very tenuous gas of charged particles. It's called a plasma. It's not the kind of plasma that you run into in hospitals, but we use the same word. And plasma fills much of the universe. Interstellar space is filled with plasmas, and interplanetary space is filled with plasma. So we're seeing the ions and electrons of the corona, of the coronal plasma, and they're scattering sunlight, and that's why we can see the form of the magnetic field lines. And these particles just can't get very far away from a field line they start on. So here's an image of the sun taken by imagers on a spacecraft called TRACE. In order to help orient you, this is just a piece of the sun. I've shown you for size reference the boundary of the sun, of the solar disk that you're seeing. So you're seeing only a little part of the surface of the sun. But this is not real time, it's speeded up. But what you can see is that the magnetic field of the sun even is very complicated. This is just a very small piece of the solar surface you're seeing. It's very variable in time, and it seems to burst out. It's a little bit like watching a pot of boiling water. There's always something different at the surface. So that's the source of the corona, and it rises above the sun. Here you're just seeing only a fraction of a solar radius, but in the surroundings of the sun, the corona goes out many solar radii. And the complex coronal structure, as I have mentioned, arises from the complexity of the solar magnetic field. And you can see they give, if you look at an object long enough, you want to give names to things. And so solar scientists give names to all of these things. You don't really have to know all of them, but what I need to show you is some of the structures just seem to have bright lines that rise from the solar surface and fall back. That's kind of like our Earth's dipole field, that it rises and comes back. But some of it looks as if it's sort of going on forever. And that is, in fact, what's happening. The plasma is so hot that it's blowing away from the sun, and it carries the magnetic field with it and stretches it out. So those magnetic fields are being stretched by the gases, which ultimately reach, as I said, a couple of million miles an hour and stretch the field into almost radial structures. And so that's the first magnetic structure I wanted to introduce, but the thing that's particularly nice about it as a starting point is that we think we can see those magnetic fields. Elsewhere in the universe, there are magnetic fields surrounding the planetary bodies in the interplanetary space, and they're all threaded with magnetic fields that we can't see. But they do, by going with spacecraft into the space around the planets, we have learned a great deal about their structure and their dynamics. Now, early on in 1600, William Gilbert discovered that the Earth had a magnetic field that looked like that of a magnetized sphere. And he drew a picture showing the direction of the magnetic field at each point of the surface of the sphere. But it took a long time after that for people to realize that the magnetic field of the Earth extended into the space above the surface, and that its structure was playing a major role in governing a lot of the dynamical activity of the upper atmosphere. One of the early hints came from radio frequency bursts, and I hope that you will be able to hear my... So when radios first became significant in modern warfare, and this was World War I, they turned on the radios, and every once in a while they would hear sounds like that. And they thought, oh my God, we're under attack. But it turned out that that was noise coming from space. We call it whistlers. And often when I give a talk, the audio part doesn't work, so I have to do it by whistling myself. I've spared you from that because of the good technical support I have here in this. So the radio waves are generated by lightning in the opposite hemisphere. So if you hear these whistler waves in the northern hemisphere, you're probably hearing a sound that was generated someplace in the southern hemisphere and followed a magnetic field line all the way to where you're standing. Well, space exploration showed us that the space is filled not only with the magnetic field, but also with magnetized plasma. And here's an example, is the famous Van Allen belts, discovered at the beginning of the space age, very energetic particles trapped in the magnetic field. If there weren't a magnetic field there, they'd just be things in space without any structure. So it's the magnetic field that's making that structure. And more recently, we recognized that there were lots of effects, not just whistlers, but energetic particles moving through space, and when they become particularly energetic, maybe driving currents through some of the spacecraft that allow us to carry cell phones and talk to each other. Sometimes they get knocked out when the intensity of the radiation gets too high. Sometimes they drive currents in the upper atmosphere that are so strong that they can cause perturbations in ground-based transformers and produce power outages. So we're beginning to study how these effects governed by Earth's magnetic field can greatly affect our near-Earth environment. And some of the ways in which it affects us are immediate. So the interference with radio communication, sometimes it causes problems with GPS and serious problems for aircraft. Some of them are long-term, and we're still trying to figure out how many of these electromagnetic effects from space are playing a role in climate change. But that's an area of great interest today. So what causes these phenomena? Well, before I start talking about what causes them, I'm just going to show you something about how we know as much as we do about what causes them. We have an armada of spacecraft. These are mostly spacecraft that are actually functioning at the moment or have just recently ceased functioning. We have lots of spacecraft in near-Earth regions. We have Voyager spacecraft was launched in the 70s and is now at the edge of the solar system, actually in interstellar. One of them is in interstellar space. A lot of these spacecraft that are shown out here are monitoring the sun. So that's one group of sources of the information that I'm going to be talking about. But I'm also interested in planets other than Earth. And we have a second armada of spacecraft that are investigating other planets. Some of this is not only present, but future. The Europa Clipper is, if we're lucky, will be launched in about 2024. NEOWISE is a spacecraft that is keeping an eye on near-Earth asteroids and trying to characterize asteroids that are on orbits that might hit Earth. Juno is a fairly new spacecraft in orbit about Jupiter. Cassini was in orbit around Saturn until September of this year. So we've learned a lot even about Earth's environment by comparing it with what's going on at other planets. Okay, so this is the source of a lot of the information I'm trying to convey. But let's go back to the corona, because the corona is the source of what we call the solar wind. It's a plasma that flows outward, radially outward throughout the whole solar system. And this is an image taken by the SOHO spacecraft, and you can see it's an artificial eclipse. The sun is this big, and they've put a shield in front of the imaging camera that's 3 times the radius of the sun. So they've blocked out the sunlight, and what you see is the plasma streaming out. And if you look very carefully, this particular one has a comet that's coming in. I'm looping it so it keeps coming in, but it comes in here and goes around the sun. There's a bright spot that's a comet. passing in front of the sun. I love that one. Okay, so then the solar wind flows through interplanetary space, and as it expands, it interacts with any body that is that is moving in the solar system. And there's a particularly interesting response when a comet is moving through the solar wind, because comets often are seen to have two tails. There's a dust tail that here is showing in white, and there's a plasma tail that's going off in an entirely different direction that's shown in sort of a bluish color. Well, the dust is blown off, it's blown away from the sun, but it still remains fairly close to the orbit of the comet. This is the orbit of the comet. So it lags the comet in its orbit, and it has a little bit of velocity that's taking it radially away from the sun. But the dust tail, the ion tail I call it, is really stretching out radially from the sun. This is the direction to the sun. The solar wind is blowing charged particles, and it doesn't affect the neutral particles. So the dust is mostly neutral, but the plasma is picked up by the solar wind. So it's really a dramatic result, the dual tail of a comet. Now, something different happens if the body that's in the solar wind has a magnetic field. The magnetic field actually excludes the solar wind. So what you have is a cavity there. This is meant to be Earth. This is Earth's magnetic field. It's blocking the solar wind from coming all the way to Earth. And this cavity is what we call a magnetosphere. It's a cavity formed in the solar wind by the magnetic field of a planet. And what you can see is the solar wind itself has magnetic fields. They're shown in gray. The body has a magnetic field shown in red. In most low-latitude regions, the magnetic field of the Earth starts in the north and ends in the south. But when you go to very high latitudes, near the poles, the magnetic field of the Earth just goes smoothly into a magnetic field line that is entering into the solar wind. So there must be something special about those high latitude regions. This whole system is pretty big. The Earth's radius is 6,400 kilometers, which is about 4,000 miles. And the magnetopause, the edge of the magnetic cavity on the day side, is about 10 Earth radii. So this is a very, very big structure. And there's lots going on inside. So I told you all about this. But the polar regions are different. And one of the signs of the difference of the polar region is the famous northern lights, southern lights, the aurora. So near the poles, the plasma is trapped in the magnetic field, and it interacts with the solar wind through a rather complex set of processes, and it forms the aurora borealis. And I like to, it's easy to look at fixed pictures, but I think it's kind of neat to look at time-lapse photography to see that the aurora changes. This is speeded up relative to real time, but the aurora comes in different colors, in different shapes, at different altitudes, and all of that is a signature of something happening farther above the Earth than the roughly 100 kilometers at which all of this activity is happening. And one of the big mysteries has been to understand how that aurora is generated. And I will spare you the details, but try to give you the big picture. So let's look at how we early on began to understand what was going on with the solar wind. There was a Norwegian scientist named Christian Birkeland who was interested in characterizing the aurora, the northern lights. He lived in Norway, so he got to see them. We don't get to see them very often. And he spent a winter on some mountains in the north of Norway and triangulated to find out the altitude of the aurora. Even that wasn't known when he started. And he was able to figure out that it was happening more than 100 kilometers above the surface. And he also worked out that it was driven by currents that were coming from farther up in space. He also very cleverly devised an experiment to allow him to see what was happening. He put a magnetized sphere, which he called a terrella, a little Earth, in a stream of charged particles, which he could generate in the lab. And he found very interesting results. For one thing, he found that there was a crown of light around each pole, just where I showed you that those magnetic field lines are beginning to link to the solar wind. So that was a major step forward to have some guidance in knowing what was going on. I have to say that many scientists ignored these results. And that's a lecture in itself. And David Southwood could give it. So it's actually a bit more complicated than just a bunch of particles coming from space. But from Birkeland's time, we learned that there is a plasma and a magnetic field present in space that forms a barrier to the solar wind, but we didn't know how far this barrier was above the surface, what its shape was, how it produced the aurora, and it was measurements by that collection of spacecraft that I showed you that really clarified what was going on. So I'm going to show you a cartoon magnetosphere responding to a dynamically changing solar wind. The details are complex, but we can use this kind of to get a roadmap. So the image that you see here is supposed to be a piece of the surface of the sun, and one of those bubbles of magnetic field is going to erupt in this region. And no, now it's right in front of you. It's going to generate a special pulse that will go through, hit the Earth's magnetosphere, and ultimately produce northern lights in the polar region. So this is just a sort of shorthand way of seeing how the solar wind can affect the surroundings of Earth, drive currents into the upper atmosphere. Well, Earth gave us the first example of a magnetosphere, but deeper understanding came by looking at magnetospheres of other magnetized planets. And it's interesting to notice that in this schematic of the magnetic fields of the planets, we lack an entry for Venus. We lack an entry for Mars. Neither of them has a large-scale planetary magnetic field. But Mercury, Earth, Jupiter, Saturn, Uranus, and Neptune all do. You can see by the peculiar orientation that some of these magnetic fields are very different from the magnetic field of Earth. But they're all embedded in the solar wind, and they all form magnetospheres. And each one is fascinatingly different. partly because their magnetic fields are different, partly because the solar wind changes with distance from the sun, partly, there was a third thing I was going to say that I've now forgotten. So the, oh yes, and partly because the effects of rotation of the planet are very important, and the outer planets rotate, they're immense and they rotate very rapidly, so that plays a major role. So an example of the magnetosphere of an outer planet comes from a neat simulation done by my colleague Shinja Jia, and we discovered with the Cassini spacecraft that Saturn is highly dynamic, even in a steady solar wind. So it isn't just the solar wind, and here is Shinja's simulation of what a cut through the noon-midnight meridian of Saturn's magnetosphere must look like, with all of this activity going on, not driven by the solar wind, but driven by the planet. And we're still trying to understand what there is about this planetary atmosphere that makes the magnetosphere of Saturn work the way it does, change the way it does. And once we figure it out at Saturn, I have a very strong feeling that we're going to discover the same phenomena at other magnetospheres. My first candidate is Jupiter. I think Jupiter is probably doing the same thing, but it's much more subtle and masked by other things that are going on at Jupiter. All right, so then I've talked about how the solar wind affects the planets of the magnetized planets of the solar system, but the solar wind is blowing out into the plasma of interstellar space. And that plasma of interstellar space is going to stop the outflow of the solar wind and create a structure, a magnetic structure, within the local interstellar medium that we call the heliosphere, that's kind of a very, very big magnetosphere. And the Voyager spacecraft spent many, many years. It was launched in the early 70s, and just last year got into interstellar space after having spent years asking, are we there yet? There's a second Voyager spacecraft that is on the verge of entering interstellar space, and Len up there probably knows whether it has or not, but I don't. So, all right. So magnetosphere-like structures exist even beyond the solar system. Here is a pulsar that has been imaged, and the boundaries that we identify at Earth's magnetosphere and at the heliosphere are there. There's an upstream shock, and there's a termination shock, and it looks a lot like what we have seen for the heliosphere. So the boundaries were observed by Chandra, the Chandra spacecraft, which is an X-ray imager. And we see these different boundaries, and the whole system is moving relative to the interstellar medium, and that's what causes the bow shock. Well, I started with the solar corona, and I want to end with the solar corona. I mentioned that I took my family to see a total eclipse. It was visible. There's going to be another one in 7 years that will be visible in the United States. It will go south-north this time, starting in Texas and going on to Maine. And I hope you'll think about the influence of coronal plasma on our home in the solar system when you see it. I'm going to show you the group watching the approaching totality. You'll see these people are looking away and toward because they want to see totality approaching, and then turn around, put your glasses back on, and look at the sun. And it's getting cold, it's getting dark. And now everybody, take your glasses off, and everybody's pointing. It's so exciting. If you missed it, don't miss the next one. Temperature really changes. It's quite remarkable. And this is a little bit faster than real time, but the sun will come back. Here it comes. And, some of us just didn't want to take our glasses and put our glasses back on. My granddaughter burst into tears. So it's really an exciting thing to see. So thank you, and time for questions.
Thank you. Am I audible? Yes? Great. Thank you for making this event possible. This is the best kind of interdisciplinarity. I highly recommend all mother-daughter teams to present together. And it's also a big adventure to come up to North Campus, so thank you for that. So first of all, you've heard about my mother, and you've heard her speak, so you know that it was quite a household to grow up in. I grew up in a household where a high-powered space physicist mother was just what moms were, where she was glamorous and stylish and would come home after a long day of teaching and lecturing and researching and produce gourmet dinners while always wearing high-heeled shoes. And the guests were always a fascinating mix of Nobel Prize winners and international scientists. And through those dinners, I met my first Russians, which I think probably precipitated the rest of my career. So I think my task today is to eke out some of the stories about my mother's life and career trajectory that may not normally come out. And from my perspective, her experience as a woman in science is particularly of interest. So there will definitely be a skew to my questions. So I wanted to ask you, first of all, about how your parents responded when you decided to go into physics. I know there was a moment where you thought about going into medicine, and your orthopedist father had strong opinions on that. So I'll let you
going to start me with that.
Yeah.
Yeah. So my father was quite determined that I should not go into medicine because his statement was, women who go into medicine lose their femininity. That was the kind of background that I came from. On the other hand, he married my mother because she knew something about physics, so it was a little bit contradictory. And I think that when I informed him that I had decided to major in physics instead of taking the appropriate pre-med courses, he was actually relieved.
I've always loved that story. That's how she found a feminine career. So then, sort of moving right along, maybe you could talk a little about your experiences as an undergraduate at Radcliffe, where when you began, women had separate courses.
Yeah. So for those of you who may not be quite so familiar with the Harvard structure, Radcliffe was formed in the 1870s as the Collegiate Society, the Society for the Collegiate Instruction of Women. And they paid Harvard professors to come across the Common and repeat their lectures, their Harvard lectures, for groups of women. And that persisted, as far as I know, till the beginning of World War II, when so many of the Harvard faculty were either in service or working on government-sponsored research, that there weren't enough professors to waste their time giving lectures over a second time. So that during World War II, Harvard became coeducational. I arrived in Cambridge, Massachusetts in the fall of 1946. And at this point, the war was over, and they decided that they should go back to the old system. And so I was signed up in Radcliffe sections of Harvard courses. My first physics lecture was to a group of 10 women, and the professor arrived and he said, "This morning we are meeting in Jefferson Hall in the Radcliffe yard at 10 o'clock. On Friday, you will come to Jefferson Hall in the Harvard yard at 11 o'clock. And so he just decided it was stupid to give one lecture to 400 men, and or he was doing it the other way around. One lecture to 10 women, and then go across the yard and give a lecture, the same lecture to 400 men. So our 10 women came into his class, and thereafter, I think all the physics classes were coeducational. Some of the other departments, on the equivalent of main campus, were slower in taking in switching. But by the time I was a sophomore, all the classes were coeducational. So we had different. That was one thing. We basically, my cohort basically integrated the academic part of the university, but that didn't change the situation in the dormitories. We had separate dormitories. We had separate rules. We had to be in by 10 o'clock. We were not allowed to wear trousers below on the ground floor of our dormitory or out on the street. We were supposed to be ladies. It was a very different world. But even that began to crack before I graduated. Not very much, but a little bit.
So one of the consequences of the separate rules and separate dorms was that you were not able to participate in study groups.
Yes, that was a real problem because very few women were majoring in math and physics. And the few women who were majoring in math and physics were split up among many different dormitories. So there was nobody in my dormitory who was taking the kinds of classes I was taking or even had taken the classes I was taking. And I was very, I felt that was a real problem for me because my boyfriend had a group that he studied with every night. And if he would get stuck on a problem, there was some interaction that was helpful. And that was very much not readily available to me, although I did start studying with my male colleagues before 10 o'clock.
That sounds pretty lonely, actually. So were you aware of this as something that was wrong or unfair at the time, or did you just take it as natural?
Well, I am afraid I have to confess that I just thought the world was structured that way, and I was not a firebrand. I didn't complain, and it just seemed to me that I was very lucky that I was getting what I was getting rather than complaining about what I wasn't getting. But that's partly, I mean, I'm somewhat embarrassed by that now, but.
Well, I want to ask you about that embarrassment, but I want to pause just a little longer on your educational period and get you to tell the story about the TA positions, because this is kind of mind-boggling. I just learned this story. Actually, my daughter got it out of
Okay,
Margaret.
So first place, I got married at the end of my junior year, and then my husband started graduate school, so it just seemed natural to stay at Harvard for graduate school. And, you know, all of the male students had teaching positions. So I went up to my advisor and I said, I'd like to be a TA. And he said, oh, I'm sorry, the TA position for a woman is full. There is, this was now 4 years after I had entered as a freshman. And although the big classes had already become coeducational, the sections were still separate for the Radcliffe women. So there was a section for women taking physics. And there was a graduate student who was senior to me who had the TA position for the Radcliffe section. And I was told that since that position was filled, I couldn't have a teaching position. And that is one time when I complained.
Good for you.
So, they finally agreed to let me become the grader for the quantum mechanics class, paid as a teaching assistant, but not allowed to stand up in front of the men.
Yeah, that would have been terrible.
Oh, I have to say something else, and that is that when I first began to teach, I had never had the experience of even teaching as a teaching assistant. So it was really hard to start teaching without ever having had even minimal experience.
That's amazing. I think I want to fast forward a little and ask, having survived all of that, do you think you've made a difference for women in your field?
Have I? You know, I have to say, I feel more here at Michigan than any place else that you've given me a chance to reach out to the women students. And that's been a really very special feature of my being part of the University of Michigan faculty. I've really enjoyed it. I don't think UCLA has taken advantage of me nearly as much as Michigan has. So I think the answer is perhaps yes, but not as much as I might have.
Well, I have a story that suggests that you might have. So my mom's colleague, Fran Bagenal, was here giving a lecture, I think, when was that, in the fall?
Yes, I think it was this quarter, beginning of the quarter.
And she told a story that made me very proud, and also, I think, showed the power of being able to subvert the old boy network in that famous alternative space, the women's restroom. And maybe I'll let you tell that story.
Well,
or is this putting you on the spot?
You know, it's straining my memory, but I mean, I do remember having gone to an AGU meeting, American Geophysical Union meeting, and having noticed a young woman who was at that time a graduate student at MIT, and she gave a really terrific talk on the Voyager plasma instrument. It was a first-rate talk, and so I got to know her. And she still, to this day, likes to talk about the 3 women who talked in that section. And she said, first there was Margie, and Margie always was dressed to the T's. Valerie's mentioned the high heels. Don't wear them anymore, but I love them.
They were good.
And the second was nicely dressed, but not quite so elegant. And then she got up in her blue jeans and blue jeans and t-shirt, and she always likes to tell how embarrassed she was about it, but she hasn't changed. She still shows up in the blue jeans and t-shirt. Anyhow, I had spotted her. She was really terrific. And I went to a meeting on magnetospheres of outer planets in Maryland at APL. And I met Fran in the ladies' room, and I said, you know, I want to introduce you to my colleague at Imperial College, David Southwood. He should hire you as a postdoc. And so she went up and she got herself introduced to David, and she got the postdoc. So there was the play in the ladies' room.
I just think it's such a revealing story because, you know, there's nothing backstage or underhanded or corrupt about it, but that's how human connections are made, and women so long didn't have that kind of access. So I think that's a great story for how cultures change. I guess, okay, I want to give you a multiple choice question for fun.
That's good. I usually do well on multiple choice.
And then ask a more sort of serious question. Okay. You have met a lot of important people through your work and your science. So, which gave you the biggest thrill? Meeting President Obama, well, people and places. Lecturing in Galileo's lecture hall in Perugia, or talking with Bill Nye, the science guy.
Well, I have to say, it was a thrill to shake hands with President Obama. I really was excited. I mean, that was such a thrill that I was willing to get up at 6 o'clock in the morning to be there 2 hours ahead of time so that the security services could make sure that I wasn't carrying a weapon or whatever. That was fun.
There's a great photograph of this occasion. It was the National Academy of Sciences Council or something like that. And it's a picture of everybody looking very awkward and uncomfortable, a whole row of short scientists, and then Barack Obama. It's quite a scene. Yeah. Okay, so here is my more serious question, and I think this is probably where we might wind down. I don't know what the timing is, but you've always had, I would say, a pretty thick skin about the kinds of slights that we were talking about in college, in graduate school, the faculty wives who gave her a hard time about abandoning her kids for this science stuff and causing irreparable damage to her children, clearly. But you've never let any of that get under your skin, and in fact, I think in most circumstances, you would say that you've never faced any kind of discrimination or troubles as a woman. And I've always admired that and felt that that's a really powerful way to to move ahead without a lot of baggage weighing on your shoulders. But right now, at this moment, it seems like a lot of people have swept things under the rug in terms of the treatment of women in professional circumstances. And I wonder if we've talked about this a little, so I'm not springing it on you cold, but whether that's given you pause or made you think that maybe it would have been good to fuss more about that TA ship or more about that 10 o'clock curfew, or if you would just recommend, ignoring the small slights and, hopefully not encountering the big ones.
Well, it's just as hard to answer the question the second time as you did. I do worry that I have been inattentive, non-confrontational, not resisted small ways in which I see women being treated differently, particularly myself. But I just think the world is so complicated that you have to choose your battles, and that I don't feel I would have done things differently. I may be wrong in that perception, but I just think you don't have it takes too much energy to deal with lots of small slights. It's much more important to focus on the big battles. And I have tried to do that. I mean, I have worked at UCLA to identify ways in which women are being obstructed in their careers. I've worked to make sure that I think I was part of a group that worked to get an ombudsman on campus so that people who were having serious problems had somebody to go to who would be objective and not and guarantee some discretion in using information. And I think that was I think I'd do the same thing again.
Great.